What's up everyone, I'm Moneymaker and welcome back to the channel. Today we're diving deep into something we use every single second of every single day. Something so ingrained in our lives that we often take it for granted. The internet. It's this invisible yet incredibly powerful force that connects billions of us, powers our economies and shapes how we learn, communicate and entertain ourselves. But how does it actually? It seems almost magical, right? You type in a web address and boom, a whole world appears on your screen. Welcome to our deep dive into how the internet works. It's a question I get asked surprisingly often, and honestly, it's a fair one. The internet is a mind-bogglingly complex system. Think about it. A global network of computers, cables, satellites, and software all working in concert. Today, we'll break down the complex layers of technology, protocols, and infrastructure that make the internet possible. We're going to strip away some of that mystery and look at the core components, the rules of the road and the physical backbone that allows you to watch this video right now, wherever you are in the world. My goal here isn't to give you a computer science degree in 20 minutes, but to provide a solid, understandable overview. We'll cover everything from the very basics of what the internet to how your data zips across continents, the security measures keeping things safe, and even a peek into what the future might hold. So grab a seat, maybe a coffee, because we're about to unpack one of the most incredible inventions of our time. Let's get into it. Alright, so to kick things off, let's establish a baseline. What the internet? At its absolute core, the internet is a network of networks. It's not a single entity, not one giant computer owned by one company. Instead, imagine countless smaller networks. Your home Wi-Fi, your office network, the network of your internet service provider, university networks, government networks, all interconnected on a global scale. It's this massive, sprawling web that allows a computer in your home to communicate with a server potentially thousands of miles away, almost instantaneously. This interconnectedness is the fundamental concept, the magic that allows these disparate networks built with different hardware and software to talk to each other comes down to one key thing: standardized protocols. Think of protocols as a common language, a set of rules that every connected device agrees to follow. These rules dictate how data should be formatted, addressed, transmitted, routed, and received. Without these standards like TCP/IP, which we'll talk more about later, it would be chaos. Each network would be an isolated island, unable to share information or services with the outside world. So it's this agreement on communication methods that truly makes the global internet possible. So when you connect your smartphone, your laptop, your smart TV, or even your smart fridge to your Wi-Fi, you're essentially joining your small local network. This local network, usually managed by your router, then connects to a larger network, that of your Internet Service Provider, or ISP. Your ISP, in turn, connects to even larger regional, national, and international networks, forming these massive backbones that carry data across continents and oceans. It's a hierarchical structure, but also incredibly distributed, which is part of its resilience. This network of networks concept is crucial. It means there's no central point of control for the internet as a whole, which is both a strength and a source of complexity. It allows for incredible scalability. New networks and devices can be added relatively easily. It also means that if one part of the internet goes down, data can often be rerouted through other paths, much like traffic finding alternative routes when there's a road closure. This distributed nature is a design philosophy that has served the internet well since its early days. The devices connected to this global network are incredibly diverse. They range from massive servers housed in data centers that store websites and power applications, to the personal computers and smartphones we use daily. There are also routers, switches and modems, specialized hardware whose job it is to direct and manage the flow of data. Each of these devices, big or small, plays a role in the internet's ecosystem, identified by a unique address, allowing data to be sent and received accurately. Ultimately, the internet is an infrastructure, a global system that provides the pathways for digital information to travel. It's the foundation upon which countless services are built. The World Wide Web, which is the same as the internet, by the way, the web is just one application of the internet. Email, streaming services, online gaming, cloud storage, and so much more. Understanding it as this foundational layer of interconnected networks using common languages is the first big step. So you've got this massive network of networks, but what actually happens when you want to access something like, say, your favorite website or, this YouTube video? Let's walk through that journey step by step. It all starts with you, the user, typing a URL like youtube.com into your browser's address bar and hitting enter or clicking a link. That simple action kicks off a surprisingly complex chain of events that happens in milliseconds. Your browser first needs to figure out where youtube.com actually lives on the internet. This is where the domain name system, or DNS, comes in. Think of DNS as the internet's phone book. Humans are good with names like youtube.com, but computers prefer numbers, specifically IP addresses, like 172.217.160.142. Your computer sends a query to a DNS server, which might be one provided by your ISP or a public one like Google's or Cloudflare's. This DNS server looks up the name youtube.com and finds its corresponding IP address. If your local DNS server doesn't know, it asks another one, and so on, up a hierarchy of DNS servers until the address is found and returned to your browser. Once your browser has that IP address, it knows where to send its request. It then crafts an HTTP request, Hypertext Transfer Protocol, which is basically a message asking the server at that IP address for the web page you want. If you're on a secure site, look for the little padlock and HTTPS. This request is encrypted using HTTPS for security. This request, along with information like what browser you're using and what specific page you're after, is then broken down into smaller pieces called packets. Each packet gets a header with information like the source and destination IP addresses and a sequence number. These packets don't just magically float to the server. They are sent out from your computer through your local network, your router, and then onto your ISP's network. From there, a series of specialized computers called routers take over. Each router examines the destination IP address on the packets and decides the best next hop to send them on their journey towards the target server. Packets from the same message might even take different routes to get to the destination, especially if there's network congestion or an outage along one path. This is the beauty of packet switching. Eventually, these packets arrive at the destination server. In our example, one of YouTube's many servers. The server receives these packets and, using the sequence numbers in their headers, reassembles them back into the original HTTP request. The server then processes this request. This might involve running some code, fetching data from a database, or simply grabbing the files that make up the web page: HTML files for structure, CSS files for styling, JavaScript files for interactivity, and images or videos. The server then sends the requested data back to your computer, again broken down into packets, each addressed to your computer's IP address. These packets travel back across the internet through various routers to your ISP, your router, and finally to your computer. Your computer's networking software reassembles these packets. Your web browser then takes all these reassembled files, the HTML, CSS, JavaScript images, and interprets them to render the web page on your screen. And all of this from your click to the page loading ideally happens in a second or two. Pretty wild, right? So we've talked about data zipping around, but what's the actual physical stuff that makes this possible? It's easy to think of the internet as this ethereal cloud, but it's deeply rooted in a massive, tangible, physical infrastructure. This infrastructure is a marvel of engineering spanning the entire globe, and it's what allows those data packets to actually travel. Without these physical components, the internet simply wouldn't exist. Let's start with the powerhouses, data centers. Data centers are essentially the brains and hearts of the internet. These are massive, secure buildings packed wall-to-wall with servers, storage devices, and networking equipment. This is where websites are hosted, where cloud services run, where your emails are stored, and where huge amounts of data are processed. They consume enormous amounts of power and require sophisticated cooling systems to keep all that hardware from overheating. Companies like Google, Amazon, Microsoft, and Meta operate colossal data centers, but there are thousands of smaller ones too, all forming critical nodes in the network. Then you have the arteries of the internet, the cables. While wireless technologies like Wi-Fi and cellular data are how we often connect the internet, the vast majority of data, especially over long distances, travels through physical cables. We're talking about thousands upon thousands of miles of fiber optic cables laid under our streets, across land, and crucially across the ocean floors. These submarine cables are incredible feats of engineering, bundles of glass fibers thinner than a human hair, capable of transmitting terabits of data per second using light pulses. They are the true backbone of global connectivity. Of course, you can't just plug your laptop directly into a submarine cable. That's where internet service providers, or ISPs, come in. Your Comcast, Verizon, AT&T, or your local fiber company, these are the gatekeepers. They manage the last-mile connection to your home or business, connecting you to their regional networks. ISPs invest heavily in their own infrastructure, including laying local cables, managing exchanges, and connecting to those larger internet backbone networks. They essentially buy bandwidth from larger carriers and sell it to consumers and businesses. Within these networks and at the major junctions of the internet are routers and switches. We touched on routers when discussing how data packets find their way. These are highly specialized computers whose sole job is to direct traffic. A home router connects your devices to your ISP, but backbone routers used by ISPs and large tech companies are far more powerful, capable of handling immense volumes of data and making split-second decisions about where to send each packet. Switches are used within local networks, like an office or data center, to connect devices and manage traffic flow efficiently between them. The sheer scale of this physical infrastructure is staggering. Think about the coordination required to lay and maintain undersea cables, the energy to power data centers, the constant upgrades needed to keep pace with ever-increasing demand for bandwidth. It's a continuous, massive global effort involving countless companies, governments, and engineers. And it's this combination of centralized data processing hubs and decentralized interconnected pathways that gives the internet its power and resilience. It's not just code, it's concrete, steel, glass, and silicon on an epic scale. All right, so with all this complexity, different hardware, software, networks all trying to communicate, how do engineers and developers keep it all organized and ensure things work together? One of the key tools for this is a conceptual framework called the OSI model, which stands for Open Systems Interconnection Model. Now, this can sound a bit academic, but it's super useful for understanding how different networking tasks are divided and managed. It breaks down the whole communication process into 7 distinct layers. Think of these layers like a stack, where each layer performs a specific set of functions and provides services to the layer directly above it, while relying on services from the layer below. This layered approach makes it easier to design and troubleshoot networks because you can isolate problems to a specific layer. It also promotes interoperability as long as different vendors adhere to the standards defined for each layer. Their equipment and software can work together even if the internal implementations are different. Let's briefly touch on these 7 layers, starting from the bottom. Layer 1, the physical layer. This is all about the actual physical transmission of raw data bits over a communication medium. Think electrical signals over copper wires, light pulses through fiber optic cables, or radio waves for wireless communication. This layer deals with things like voltage levels, pin layouts, cable specifications, and data rates. It's the tangible connection, the physics of sending ones and zeros. Above that is layer 2, the data link layer. This layer is responsible for reliable data transfer between 2 directly connected nodes on the same network segment. It takes the raw bits from the physical layer and organizes them into frames. It also handles error detection and correction that might occur at the physical layer and manages access to the physical medium using MAC addresses, those unique hardware addresses on your network card. Technologies like Ethernet and Wi-Fi largely operate at this layer. Next up is layer 3, the network layer. This is where routing happens. Its main job is to move data packets from a source network to a destination network, which might involve traversing multiple intermediate networks. This is the layer of IP addresses, Internet Protocol. Routers operate at layer 3, making decisions based on IP addresses to forward packets along the best path towards their final destination. It's all about logical addressing and path determination across different networks. Layer 4 is the transport layer. This layer provides host-to-host communication services for applications. The two most well-known protocols here are TCP, Transmission Control Protocol, and UDP, User Datagram Protocol. TCP provides reliable, ordered, and error-checked delivery of a stream of data, making sure all packets arrive and are in the correct order, essential for things like web browsing and file transfers. UDP is faster and connectionless, used for applications like streaming or online gaming, where speed is more critical than perfect reliability for every single packet. It also handles segmenting data from upper layers and reassembling it on the receiving end. The top three layers, Session Layer 5, Presentation Layer 6, and Application Layer 7, are often grouped together as they deal more with application-level data. Layer 5, the Session layer, manages connections or sessions between applications, establishing, maintaining, and terminating them. Layer 6, the Presentation layer, is responsible for data translation and formatting. It ensures that data sent from the application layer of one system can be understood by the application layer of another system. This includes things like character encoding, data compression, and encryption or decryption. Finally, Layer 7, the application layer, is the one closest to the end user. This is where network applications and their protocols reside, like HTTP for web browsing, SMTP for email, FTP for file transfer, and DNS for name resolution. This layer provides the interface for applications to access network services. So, while you might not consciously think about the OSI model daily, it's the underlying framework that ensures all the pieces of the internet puzzle fit together and function smoothly, from the physical cable all the way up to the app on your screen. So, we've mentioned protocols a few times, these rules of the road that allow different devices and networks to communicate. Without them, the internet would be a digital Tower of Babel. There are many protocols at play, each designed for a specific task within that OSI model framework we just discussed. Let's dive into some of the most important ones that really make the internet tick, the unsung heroes working tirelessly behind the scenes. First and foremost is the Internet Protocol, or IP. This is the principal communications protocol in the Internet Protocol suite for relaying datagrams across network boundaries. Its routing function enables internet working and essentially establishes the internet. IP is responsible for addressing hosts, giving every connected device its unique IP address, and for routing packets of data from a source to a destination based on these IP addresses. It's a connectionless protocol, meaning it doesn't guarantee delivery, but it's the fundamental addressing system for the entire internet. Working hand in hand with IP at the transport layer are TCP, Transmission Control Protocol, and UDP, User Datagram Protocol. TCP is connection-oriented, meaning it establishes a connection before sending data and ensures that data arrives reliably, in order, and without errors. It does this through acknowledgements and retransmissions of lost packets. This makes it perfect for web browsing, HTTP or HTTPS, email, SMTP, and file transfers, FTP, where accuracy is paramount. You want the whole web page, not just bits of it. UDP, on the other hand, is connectionless and much simpler. It sends packets without establishing a prior connection and doesn't guarantee delivery, order, or error checking. So, why use it? Speed and low overhead. UDP is great for applications where occasional lost packets are acceptable or can be handled by the application itself, and where real-time transmission is critical. Think video and audio streaming, online gaming, or DNS lookups. A dropped frame in a video stream is often less disruptive than a long pause waiting for a retransmission. For accessing the World Wide Web, the STAR protocols are HTTP, Hypertext Transfer Protocol, and its secure version, HTTPS. HTTP defines how messages are formatted and transmitted, and what actions web servers and browsers should take in response to various commands. When you type a URL, your browser sends an HTTP GET request to the server. HTTPS adds a layer of security on top by encrypting the communication using TLS or SSL, ensuring that the data exchange between your browser and the server is confidential and integral. That little padlock icon is your friend. For sending and receiving emails, we have a suite of protocols. SMTP, Simple Mail Transfer Protocol, is used for sending emails from an email client to an email server, and also between email servers. When you want to retrieve emails from a server to your client, You'll typically use either POP3, Post Office Protocol version 3, or IMAP, Internet Message Access Protocol. POP3 usually downloads emails to your device and removes them from the server, while IMAP synchronizes your emails across multiple devices, keeping them on the server. And finally, a really crucial but often invisible protocol that keeps the Internet's core routing infrastructure working is BGP, Border Gateway Protocol. BGP is used by ISPs and large organizations to exchange routing and reachability information between their autonomous systems, essentially large networks. It's how routers on the Internet backbone learn the paths to various networks across the globe, allowing them to make efficient decisions about where to forward traffic. It's complex, but vital for the Internet's global routing. These are just a few, but they form the bedrock of Internet communication. All right, so we have this incredible global network, data flying everywhere, connecting billions of devices and people. That's amazing, but it also opens up a whole world of potential security risks. With so much personal, financial, and critical information online, Internet security isn't just an afterthought, it's absolutely essential. There are numerous technologies and practices in place designed to protect data, privacy, and the infrastructure itself. Let's look at some of the key digital bodyguards. One of the most fundamental security measures you interact with daily, probably without even thinking about it, is TLS or SSL, Transport Layer Security or Secure Sockets Layer. This is the technology behind HTTPS. When you see that padlock in your browser's address bar, it means your connection to that website is encrypted. TLS or SSL creates a secure encrypted tunnel between your computer and the web server, ensuring that any data exchanged, passwords, credit card numbers, personal messages, is scrambled and unreadable to anyone who might try to intercept it. It's a cornerstone of secure web communication. Next up are firewalls. A firewall acts as a barrier between a trusted internal network like your home or corporate network and untrusted external networks like the Internet. It monitors incoming and outgoing network traffic and decides whether to allow or block specific traffic based on a defined set of security rules. Firewalls can be hardware devices, software programs, or a combination of both. They are your first line of defense, preventing unauthorized access and blocking malicious traffic before it can reach your systems. For enhancing privacy and security, especially on public Wi-Fi networks, many people turn to VPNs or virtual private networks. A VPN creates an encrypted tunnel between your device and a VPN server operated by the VPN provider. All your internet traffic is routed through this tunnel, masking your real IP address and making it much harder for others, like your ISP, advertisers, or malicious actors on a public network, to track your online activity or intercept your data. It's like creating a private, secure lane for your data on the public internet highway. Of course, we can't talk about security without mentioning antivirus and anti-malware software. These programs are designed to detect, prevent, and remove malicious software, viruses, worms, trojans, ransomware, spyware from your computers and devices. They work by scanning files and programs, monitoring system behavior for suspicious activity, and comparing code against databases of known malware signatures. Keeping your antivirus software up to date is crucial as new threats emerge constantly. It's your endpoint protection in larger organizations and networks. More sophisticated systems like IDS, intrusion detection systems, and IPS, intrusion prevention systems, are often deployed. An IDS monitors network or system activities for malicious activities or policy violations and produces reports to a management station. An IPS goes a step further. Not only does it detect malicious activity, but it can also take action to block or prevent it, such as dropping malicious packets, blocking traffic from offending IP addresses, or resetting connections. These are like advanced security guards constantly patrolling the network. Beyond these technologies, good security also involves practices like using strong, unique passwords, enabling two-factor authentication, being cautious about phishing scams, and keeping your software and operating systems updated to patch vulnerabilities. Security is a layered approach. No single solution is foolproof. It's a continuous cat-and-mouse game between those trying to protect systems and those trying to compromise them. But these tools and practices are vital for making the internet a safer place to operate. The internet isn't static, it's constantly evolving. New technologies are always emerging, building upon that foundational infrastructure we've discussed to deliver richer, faster, and more integrated experiences. These modern internet technologies are changing how we store data, access content, connect devices, and interact with the digital world. Let's explore a few key players that are defining the internet of today and paving the way for tomorrow. So, first up is cloud computing. You hear this term everywhere, and for good reason. Essentially, cloud computing means accessing computing resources like servers, storage, databases, networking, software, analytics, and intelligence over the internet, the cloud, on a pay-as-you-go basis rather than owning and maintaining physical data centers and servers yourself. Companies like Amazon Web Services, AWS, Microsoft Azure, and Google Cloud Platform are a huge part of this, offering incredible scalability and flexibility. This has revolutionized how businesses operate and how services are delivered. Closely related to making your online experience faster are content delivery networks, or CDNs. When you watch a video on YouTube or Netflix, or load a popular website, chances are you're accessing content from a CDN server that's geographically closer to you, rather than the original server, which might be thousands of miles away. CDNs work by caching, storing copies of content like images, videos, and static web files on multiple servers distributed around the world. This reduces latency, speeds up load times, and reduces the load on the origin server, leading to a much smoother user experience. Another significant, though perhaps less visible to the average user, development is IPv6. We mentioned IP addresses earlier, the unique identifiers for devices on the internet. The original system, IPv4, uses 32-bit addresses and can support about 4.3 billion unique addresses. Sounds like a lot, but with the explosion of internet-connected devices, we've essentially run out of IPv4 addresses. IPv6 is the successor, using 128-bit addresses, which provides a virtually inexhaustible supply of IP addresses, something like 340 undecillion. The transition is ongoing, but crucial for the internet's continued growth. Then there's the Internet of Things, or IoT. This refers to the ever-growing network of physical devices, from smart home appliances like thermostats and refrigerators to wearables, industrial sensors, connected cars, and medical devices that are embedded with sensors, software, and connectivity, allowing them to collect and exchange data over the internet. IoT is transforming industries and creating new possibilities for automation, monitoring, and control, but it also brings new challenges in terms of security and data privacy that need careful consideration. We're also seeing the rise of edge computing, which is a distributed computing paradigm that brings computation and data storage closer to the sources of data, like IoT devices or local edge servers. This is done to improve response times and save bandwidth, as opposed to sending everything to a centralized cloud. It's particularly important for applications requiring real-time processing like autonomous vehicles or augmented reality. It complements cloud computing by processing data locally where it makes the most sense. And of course, artificial intelligence, AI, and machine learning, ML, are increasingly intertwined with the internet. AI algorithms are used for everything from personalizing your news feeds and search results to powering recommendation engines, detecting spam and malware, optimizing network traffic, and enabling sophisticated voice assistants. The internet provides the vast data sets AI needs to learn, and AI in turn is making internet services smarter and more efficient. These technologies are not just trends, they are fundamental shifts in how the internet operates and what it can do. We've talked a lot about the internet as a global network, but how does it connect countries separated by vast oceans and diverse terrains? It's not just magic, it's a colossal feat of engineering and international cooperation. The physical links that tie the world's internet infrastructure together are truly remarkable. And two key components play starring roles: submarine cables and internet exchange points, IXPs. These are the unsung heroes, enabling you to connect with someone on the other side of the planet. The absolute backbone of intercontinental internet connectivity is an extensive network of submarine fiber optic cables. These aren't your average household cables. These are heavily armored, technologically advanced conduits laid across the ocean floors, spanning tens of thousands of miles. Specialized ships lay these cables, which can rest as deep as Mount Everest is tall. Inside are multiple pairs of optical fibers, each capable of carrying enormous amounts of data as pulses of light. Companies and consortiums invest billions in these projects, creating the superhighways for global data traffic. Think about it. When you access a website hosted in Europe from the US, or make a video call to someone in Asia, your data is likely racing through several of these undersea cables. There are hundreds of such cables crisscrossing the globe, forming a redundant and resilient mesh. If one cable is damaged, say by a ship's anchor or a natural event, traffic can often be rerouted through other cables, though sometimes outages in specific regions can still occur. The capacity of these cables is constantly being upgraded to meet the insatiable demand for international bandwidth. Now, once data reaches a country or a major metropolitan area, how do different internet service providers, ISPs, within that region efficiently exchange traffic with each other and with content providers? This is where Internet Exchange Points, or IXPs, come in. An IXP is a physical location, typically a data center, where multiple ISPs and content delivery networks, CDNs, connect their networks directly. Instead of routing local traffic through distant, potentially congested and expensive transit providers, they can exchange it locally at the IXP. This direct peering at an IXP has several benefits. It reduces latency because data takes a more direct path. It can lower costs for ISPs as they don't have to pay transit fees for traffic exchanged locally. And it improves the overall efficiency and resilience of the internet within that region. Major cities around the world have large IXPs that act as critical hubs for regional internet traffic. They are neutral meeting points that facilitate the smooth flow of data between otherwise competing networks for the benefit of all their users. The placement and capacity of both submarine cables and IXPs also have geopolitical and economic implications. Countries with robust international connectivity and well-developed IXPs are better positioned to participate in the global digital economy. There's a constant drive to build new cable routes to connect underserved regions and to increase redundancy to existing ones. It's a complex ecosystem involving private companies, governments, and international organizations, all working to weave this global web tighter. So while your local Wi-Fi gets you onto the internet, it's these massive submarine cables and strategically placed IXPs that truly make it a worldwide phenomenon. They bridge the physical distances, enabling the seamless flow of information that underpins our modern connected society. The scale of this infrastructure is often hidden from view, buried under oceans or housed in unassuming buildings, but its impact is felt by billions every day. It's the plumbing that makes the global village possible. So we've journeyed from the basics of what the internet is, through its intricate workings, to the massive infrastructure that supports it. But the internet, as we know, never stands still. It's a constantly evolving entity, and the horizon is buzzing with emerging technologies that promise to reshape it yet again. What does the future hold? While crystal balls are notoriously unreliable in tech, we can look at some of the key trends and innovations that are poised to define the next era of the internet. One of the most immediate and impactful evolutions is the continued rollout and advancement of mobile network technology, specifically 5G, and the development of 6G. 5G offers significantly higher speeds, lower latency, and greater capacity than 4G/LTE. Enabling a new wave of applications from enhanced mobile broadband and immersive AR/VR experiences to massive IoT deployments and critical communications for things like autonomous vehicles and remote surgery. 6G, though still in the research phase, aims to push these boundaries even further, potentially integrating AI more deeply and exploring new frequency bands. Looking further out, we have the fascinating, though still highly theoretical, concept of the quantum internet. This wouldn't replace the classical internet we use today for browsing or streaming, but rather complement it for specialized tasks. Leveraging principles of quantum mechanics like entanglement and superposition, the quantum internet could enable ultra-secure communication that's fundamentally unhackable, as well as connect quantum computers to solve problems currently intractable for even the most powerful supercomputers. It's early days, but the potential is transformative. Another major trend is the push towards a more decentralized web, often referred to as Web 3. This movement aims to shift power away from large centralized platforms and back towards individual users and creators. Technologies like blockchain, cryptocurrencies, decentralized autonomous organizations, DAOs, and peer-to-peer protocols are foundational to this vision. The goals include greater user control over data, enhanced privacy, censorship resistance, and new economic models. It's a complex and sometimes controversial space, but it represents a significant rethinking of the Internet's architecture and governance. Artificial intelligence will undoubtedly play an even more profound role in the future Internet. We're already seeing AI optimize network performance, enhance cybersecurity, and personalize user experiences. In the future, AI could manage vast, complex networks autonomously, enable more intuitive and natural human-computer interfaces, and drive the development of entirely new Internet services and applications that we can barely imagine today. The synergy between AI and the Internet will continue to be a powerful engine of innovation. Of course, these advancements will also bring new challenges, ensuring equitable access to these future Internet technologies, addressing the ethical implications of AI and widespread data collection, managing the environmental impact of ever-increasing data processing, and establishing governance models for decentralized systems are all critical issues that will need to be navigated. The future Internet will be a product not just of technological breakthroughs, but also of societal choices and regulatory frameworks. The journey of the Internet from a research project to a global utility has been incredible, and it's clear that the pace of innovation isn't slowing down. From faster wireless to fundamentally new ways of communicating and organizing information, the next few decades promise to be just as dynamic. It's an exciting time to be watching and participating in the evolution of this technology that so profoundly shapes our world. The Internet of tomorrow will likely be even more integrated, intelligent, and perhaps more user-centric than ever before. All right, so that was a pretty comprehensive look at how the Internet works, from the foundational concepts to the physical cables under the ocean, the protocols that govern communication, the security that protects us, and even a glimpse into what the future might hold. It's a massively complex system built and maintained by countless individuals and organizations around the world, and it's something that continues to evolve at an incredible pace. Hopefully this breakdown has demystified some of that complexity and given you a better appreciation for what happens every time you go online. Thanks for joining us on this journey through the layers of the Internet. I know it was a lot of information to take in, but understanding even the basics of this technology that's so central to our lives can be incredibly empowering. From the OSI model to the role of IXPs, each piece plays a vital part in delivering the seamless digital experience we often take for granted. We've covered a ton of ground, and I really appreciate you sticking with it. If you found this video helpful, or if you learned something new, definitely let me know by giving it a thumbs up. It really helps the channel, and if you want more deep dives into technology explanations of complex topics and reviews of the latest tech, don't forget to like, subscribe, and hit the bell icon for more tech insights. We've got a lot more cool stuff planned. As always, thanks for watching, and I'll catch you in the next one. See you in the next video.